Okay, so for my pencast, I have homework 2, problem 1, as you can see up there. And the problem gives you this diagram here, which is a wave, and it gives you a velocity for each pulse in the wave. This one is moving to the right at 1 meter per second, and this one is moving to the left at 1 meter per second. And what it asks you to do is you have to draw a graph for every 1 second interval between the times of 1 and 6 seconds. This one here, the one given in the problem statement, is at 0 seconds t equals 0. Sorry, a bit of a cough. So just before even starting the pencast, I drew out 6 graphs. This one labeled t equals 1, t equals 2, and so on, all the way to t equals 6 down here. All the same axes. This is a very straightforward problem. Because it gives you the velocity of these waves, you can just kind of do some basic dimensional analysis to really just find out where it's going to be located. I'm actually not even going to do that, but it's v equals 1 meter per second. And we know, for example, t1 is going to be moving this direction. So at t1, we cancel out our seconds. 1 second. Sorry about that cough. I'm really sorry. And then we get, it now starts at 1 meter instead of 0 meters, right? So we're going to start that here. I did these in intervals of 2. So this is going to go like this. And then pulse 2 here is doing the same thing, but in the other direction. So it's actually going to go starting from 5 now instead of this one. You know, it starts at 6. All the way down to there. And there we go. So that is our graph for t equals 1. And now we're going to do the same thing for t equals 2, t equals 3, t equals 4, t equals 5, and t equals 6. So, 1 second real quick. Ow. Alright, so t equals 2. It's going to start at 2. You do the same math. Draw it up like that. It should end at 6, but now you kind of draw this dotted line here. Because it's kind of hard to see in this graph, but this is all one wave. It's not just pulses. These are joined together. We have to account for how they're going to interact with each other at this place in time. So remember, this one also should be, in theory, ending at like 5 now, actually, or 4 now. So we have it like that, but now we connect it, and we see the waves actually have kind of a different form. They're a little bit more peaked. It's hard to tell on this, but they have less width because they're connected still. And then, so that's for t equals 2. T equals 3 is actually a pretty good one. It's now at 3 for start of the displacement. So we're going to go 3 up to 7. But because they now be overlapping entirely as they move towards each other, if you know, we kind of have our dotted wave here. That's representing where the other wave would be if they weren't interfering with each other, or the other, I guess, antinode of the wave, this thing here. So that's them at their maximum interference. And then as they go back away from each other, we kind of get the same shape we saw up here, but in reverse. So this one's going up, up, up. And we draw, that's not a very straight line, my apologies. We draw a straight line over here to 6 to indicate where it would be. I'm going to start the other wave too, just so this works out better. I had to condense my graphs too to fit them all on one page, sorry about that. And then we draw our dotted line, and then we connect our 2 waves. See how it's kind of the same for t equals 4, it's like the inverse of t equals 2. As they keep traveling apart, we now have them starting at 1 again, but on the negative pulse. There's our 1 wave. Oh shoot, I drew that wrong. My apologies. Okay, so there we go. 1 to 5, right? Because remember from here, it's 0 to 4, and it's just kind of moving in one direction by 1 meter each second, and because we're only moving by intervals of 1 second. And I'm going to draw this up. And now our positive wave is ending at 9 instead of our negative wave, like in t equals 1. And now for the last one at t equals 6, it's going to resemble exactly what we started with at t equals 0, but once again, just like everything else so far, it will be inversed. So 0, boy. 0 to 4 again. You can't quite see the bottom there. And then 6 to 10 for our positive phase. Yeah, and that's the entire problem. It's pretty straightforward. The key to it is really just looking at... Oh, I lost my... Shoot, this is hard to film. But yeah, so the key to it is looking at the direction of the wave and the units it's in, canceling those units to get what you want, which in this case is our meters, and the displacement stays constant for all of it. So thank you for watching my pencast. I hope it was helpful. Bye.